Right, hello folks, welcome to the next little video. They say they're not very little, sorry about that. Chemistry is full of exciting knowledge to learn. This one has a relatively small amount of new content, I guess, but just to keep your learning happening, I'm just going to start with a few questions based on some of the things that we've done before in these videos. So just a little quiz effectively, some shorter, some longer questions. So question one is, if you had the species NH2, is this a radical or not? So pause the video, see if you can figure that one out and explain your answer. And you should say yes, it is. And the best way to always is to do a dot cross diagram. Nitrogen is in group 15, 5 of its own electrons. Always spread them out between kind of 4 possible pairing positions. And then the hydrogens will bond on to will pair up with 2 of them. And so that leaves an unpaired electron there like that. Question 2, then, longer question. If a bond XY, doesn't matter what the substances are, has a bond enthalpy of 258 kilojoules per mole, calculate the longest wavelength of light in nanometers that can photodissociate it. Okay, this uses a bit of information from the data sheet. So just in case you don't have the data sheet to hand, I will just tell you that we've got Planck's constant. (6.63 times 10 to the minus 34). And Avogadro's constant, or Avogadro, should say it in Italian accent, really. He was Italian, had a great name. Not just the Avogadro bit. Anyway, is that, so there we go. Pause the video, see if you can remember the steps. It's a multi-step calculation, a fair bit of logic to get you from bond enthalpy through to wavelength in nanometers. Have a go. Okay, so the steps are that if you start with your 258 kilojoules per mole, and you then doesn't matter quite what order you do this things in, but you are going to convert that to joules per mole, 258,000 joules per mole, and then you are going to convert that into the number of joules per bond, so 258,000 divided by Avogadro constant. Oops. Bear with me, 258,000 divided by 6.02 times 10 to the 23 is 4.286 times 10 to the minus 19 joules per bond. So we work down to a single bond, which will be affected by a single photon. So we can now figure out what that is in terms of energy, sorry, in terms of frequency. That's an amount of energy. So we can use E equals HF and rearrange to the frequency is the energy divided by Planck's constant. Yeah, Planck's constant. So we're going to take that number, we're going to divide by 6.63 times 10 to the minus 34. And that tells us that our frequency is 6.464 times 10 to the 14 hertz. And then we've got to talk about wavelength, not frequency. So we can use the C equals lambda V. Oh, my bad. Just realized that we didn't give you the speed of light either, did we? Speed of light 3.0 times 10 to the 8 meters per second. That would have been needed as well that's from the data sheet. So to work out wavelength, you can do the speed of light divided by the frequency. So 3 times 10 to the 8 divided by that answer, and that comes out to 4.64 times 10 to the 7. But that's in meters. And so then, since we want it in nanometers, each meter is 1 times 10 to the 9 nanometers. So we can times that by 10 to the 9, and it comes out to 464 nanometers. Okay, happy little skill. Number 3, one step that takes place in reaction of an alkane and halogen in the presence of UV light can be this. So can you explain what type of step in a radical reaction that represents? That's not saying is it kind of first step, second step, third step. There was a bit of vocab about different types of step in radical reactions, something about beginning things, carrying things on, and finishing things as a clue. So pause, see if you can come up with what type it is and explain your reasoning. So the answer is this is a termination step. The 3 possibilities were initiation, propagation, and termination. It's a termination step, and that's because you are going from reactants with radicals to products with no radicals. Okay, that radical mechanism of alkanes reacting with halogens is takes quite a bit of learning, so do review that as much as needed. Remember, you can always get in touch with me at any point if there's something that you're particularly stuck on. Okay, let's look at the new content for this little section then. So this is the reactivity of haloalkanes. And so the context here is, imagine that you've got this haloalkane, this haloalkane, and this haloalkane. And then you're going to react each one with hydroxide ions. So say, for instance, from sodium hydroxide solution. And so the question is, which is most reactive? And reactivity leads to reactions happening faster, not more stuff reacting, not bigger quantity, but happening at a faster rate. Which is most reactivity? No, which is most reactive is what I meant to say. So in other words, which reaction would happen fastest? Okay, now I'm not going to just tell you, I want you to pause and think. Think about the reaction with hydroxide ions. Think about the type of mechanism involved there, and what that mechanism looks like. Maybe draw out the mechanism, and then think what factors might be involved that could make one of these more reactive, one of these less reactive, one of these react faster, one of these react slower. So pause the video. I want you to do some thinking. Don't worry if you're thinking, well, I don't know, I'm not sure. That's not the point. I want you just to play with the ideas and have a think. So start the video again when you're ready. Okay. Now, generally, people come to the wrong conclusion in this thinking, and that's fine. So just make a mental note, though, this is kind of unexpected, the conclusion here. So if I remind you of the mechanism, I'll take the top one. You've got the haloalkane, it's got the delta plus carbon and the delta minus halogen, and then if we attack it with a hydroxide ion with its negative charge and lone pair of electrons, we get the arrow from the lone pair of electrons to the positively charged carbon, and then the existing CCl bond breaks with the electrons being pulled onto the chlorine. So what is it that drives this reaction? What is it that could make it more or less reactive? There's a couple of things going on. One is we need a delta plus carbon. Oops, not at. To be attacked. Great. So anything that makes the carbon delta plus allows this reaction to happen. The more delta plus it is, you would think, the more attractive it is to attack. So we could say, so this would lead to the thought that maybe the chloroalkane is the most reactive. Because the Cl is the most electronegative. So gives the biggest delta plus on the carbon. Okay, just think about that. Does that make sense? The reason that that hydroxide ion can attack the carbon is because the carbon's delta plus. The reason the carbon's delta plus is because it's got a halogen attached. But the different halogens have different electronegativities. The more electronegative the halogen is, the more the electrons are being pulled towards the halogen. So the more delta plus the carbon becomes. Electronegativity increases up the group. So we would expect that bond to be the most polar with CCl, the biggest delta plus on the carbon, and hence the most, it's the most open to attack by the hydroxide ion. However, that's not the only factor. The only reason this reaction can actually happen is because we need the carbon halogen bond to break. It's all very well that hydroxide ion being attracted to the delta plus carbon and sort of trying to form a bond to it, but that's not going to happen unless the existing bond will go. Because carbon can only do 4 bonds. So in order for this reaction to happen, not only do we need the delta plus carbon, but we need the carbon halogen bond to break. So now we've learned some principles about bond strength before. Not that you need to know the strength of every single bond, but for covalent bonds, there was a factor that directly affected the strength of a bond. Do you remember what that was? Just pause the video. Between those different halogens, chlorine, bromine, and iodine, can you remember anything that would allow you to predict which one of those bonds would be stronger and which one of those bonds would be weaker or weakest? Okay, and the thing you should have remembered is bond length. The smaller the atom, the closer the atoms can get shorter bonds, and so stronger bond. So this one has the shortest bond, Oh, actually, I won't write it in here. So yeah, we need so let's add maybe the iodopropane. 2-iodopropane is most reactive. Because iodine is the biggest atom. So makes the longest and hence weakest covalent bond. Less energy needed to break it. So a lot of life is limited by the amount of energy available. And hence, if something requires a lot of energy, it's less likely to happen. So we've got two conflicting things here. If what controls reactivity is the size of the delta plus on the carbon, hence how open it is to attack, then it will be the 2-chloropropane that's most reactive. If, however, it's the bond strength of the carbon-halogen bond that controls reactivity for haloalkanes, then it'll be the 2-iodopropane that's most reactive. And so what is the answer? And the answer is that this is the controlling factor. So there you go. It is not the how delta plus the carbon is. It is the bond strength of the carbon halogen bond. So we can say that haloalkanes increase in reactivity as you go down group 7. In other words, they will nucleophilic substitution will happen faster down group 7. Okay, there is one little extra thing that you have to do here. You need to be aware of how this could be investigated in the lab. So investigating haloalkane reactivity practically. And if I was with you, I would have done a little demonstration of this. There's not much to see, to be honest. Try and remind me at the beginning of next year. I'll show you. Investigating. And so here's what you do. You get a test tube, and into that test tube, you put a mixture of things. You put your haloalkane, you put your ethanol, you put some ethanol, and you put some silver nitrate solution. Why would you do that? You might be asking. Let's explain that. So the haloalkane is, this is. Excuse me a moment. This is the thing being investigated. So this is your very different haloalkanes and see the effect on rate. So that's fair enough. That's literally what you're investigating. You're investigating haloalkane. Sorry, just realized I'm descending into writing rubbish. Reactivity, practically. Why the ethanol? The ethanol just acts as a solvent, allowing the haloalkane and the AgNO3AQ to mix. So you get that quite often in organic reactions. You get what's called a common solvent, something that will allow one reactant to mix with the other reactant. A lot of organic liquids don't mix with water. So if you've got a reactant that dissolves in water, then the problem is it will sit as a separate layer to your organic substance, and that makes the reaction complicated because they're just not meeting. You have to sort of constantly like be shaking it. The ethanol, both things dissolve in the ethanol, so it kind of allows them to meet. So it doesn't actually take part in the reaction. So this is not a reactant itself, just a solvent. What about the silver nitrate solution then? So this supplies water to react with the haloalkane. Remember, one of the haloalkane reactions is with water. And it supplies Ag+ ions. Why would we do that? Which will precipitate with any halide ions that form. Okay, so what we're setting up here is a reaction between a haloalkane and water. The silver nitrate solution supplies water. So this is a nucleophilic substitution of a haloalkane. The water knocks off the halogen, replaces it with an alcohol group. The ethanol's there to bring the two things together. And the silver nitrate supplies silver ions as a kind of an indicator to see the reaction happening, because a precipitate will form. In other words, it will go cloudy. So what's actually going on is, so let's say we're taking 2-bromopropane, reacting with water. It will need a bit of heat, and we'll get the halogen knocked off and an OH group put on, and from the halogen coming off we'll get Br-, and we'll also get H+, where the water drops one of its hydrogens. And then as that bromide ion comes off, this reacts with Ag+. So a little revision challenge for you. Pause the video. Can you remember how to write an ionic equation for the precipitation that you get when silver nitrate solution meets halide ions in solution? Have a go. Start the video when you're ready. And what you should have written is that Ag+ AQ, so these ionic equations, we leave out spectators like the nitrate ions, plus the Br- ions AQ that are being knocked off, will make AgBr solid. And, well, there's another question. What would that look like? So this is a cream-colored precipitate. So the point here is that you heat the mixture, you time how long it takes for the mixture to go cloudy. This is obviously not a super accurate experiment, because going cloudy What does that mean? I don't know if you did an experiment like this at school, where maybe you put a piece of paper with an X under a beaker and timed how long for the X to disappear. You could do that kind of thing. And so the faster it goes cloudy, the more reactive the haloalkane must be. So we would expect an iodoalkane to go cloudy very fast because of that weak Ci bond. We would expect a fluoroalkane to go cloudy very slowly because it's a very strong CF bond. It's very short. As with all of these things, if you're asked to describe an experiment, diagrams are good, but you must also specify things to do with what measurements you take, controlling variables, accuracy, etc. So we could control things like equal moles of the haloalkane each time. Equal volume of ethanol. What else? Can you think of anything else? Think about the different factors in there that could affect how long it takes for it to go cloudy. Equal volume and concentration of the silver nitrate solution. Anything else? Same temperature. Don't say the same haloalkane each time, because the whole point here is you're comparing haloalkane reactivity. So that has to vary. Everything else is staying constant. So you would control those. You would time how long it takes to go cloudy. You can make the prediction: the faster it goes cloudy, the more reactive the haloalkane must be. Diagram-wise, it's not very significant. Accuracy here would be things like using a stopwatch to the nearest second. There's not much point suggesting any more accurate, precise than to the nearest second, because human reaction time in spotting it goes cloudy and stopping it is can't exceed that. Okay, so just the key principle from this then is that the haloalkanes get more reactive as the halogen gets further down group 7, and the reason for that is not anything to do with how delta plus the carbon is in the haloalkane, but how strong that bond is between the carbon and the halogen that has to break as the reaction happens, and that you could be asked to suggest how this could be investigated practically in the lab, and you would have to suggest exactly this. So this is actually a sort of almost set practical, though chemistry doesn't really have those, but they do it does come up relatively often, this specific thing for some reason, and there is only really one way to do it, and that's creating this kind of mixture of the haloalkane with some silver nitrate solution, some ethanol, to bring them together, and then heating it up and timing how long it takes to go cloudy. I say heating it up. The best thing to do is to have everything already up at the right temperature in a water bath before you mix them, so that they start at the right temperature and stay at that temperature throughout. And the reason this works is that you have the substitution reaction of the haloalkane with water knocking off the bromide ion, and as soon as the bromide ion forms, it can precipitate with the silver bromide, with the silver ion to make silver bromide, and that turns the thing cloudy. So we're timing to see how long it takes to go cloudy in order to determine how fast the reaction's going. The faster the reaction, the more reactive the haloalkane. So we would expect iodoalkanes to go cloudy faster than fluoroalkanes. That'll do.